what are the tools? Well, so far, we were focusing on rock mechanics, so rocks. And specifically, what we're looking at has been the rock mass. So the rock mass is the intact rock plus the fractures. So there's empirical methodologies, and we saw some of those. There's some stochastic models that we're going to soon see. And there are tools that actually are the computer models. Generally, you have different types of mathematical approach that will help to solve complex situations. One is the finite element model. Others are the finite differences. Black is a finite difference model. You have a discrete element model. So some of you, I think, was asking about UTEC. That is one discrete element code. And then you have hybrid methods that are hybrid in the sense that they combine the finite element with the discrete element, the boundary elements with maybe the discrete elements, and so on. So those are tools. And what you are going to try to use is actually to find them, to use them as you need to calibrate. It means that you need to assign the parameters. You assign the parameters by looking at laboratory tests. For example, to look if you're using a more Coulomb criteria, you're looking for the cohesion and the friction angle. And you can measure those in the lab. And on Tuesday you saw the type of test you can run to actually measure those parameters for that particular route. But then once that you are calibrating, means that your model is able to reproduce the simple experiment that you ran. You can use the same input parameters and apply or build a model that is much more complex and would try to reproduce what could be the stability of a slope, such as what you did just half an hour ago, 1 hour ago, with flag, or the stability of a tunnel. And so what you're going to use your model, your numerical model, in a predictive way. So you try to predict what is happening. One thing is that you need to always be aware that prediction gives you one single result, but you have always an uncertainty on your inputs. So probably you need to see a little bit more what if my input is a little bit different. What is if instead of using one single value, I use a range? How much that parameter is sensitive, so how much care I need to actually investigate that particular cohesion for the rock. And then there are other methodologies that we'll be touching very quickly, and I will mention is the so-called synthetic rock mass, where you actually upscale models from the lab to much larger scale to try to account for the presence of more and more features, such as it could be from the micro cracks to larger crack to joint sets to even faults at larger scale. And the last but not least, what you can use the model is really to try to understand what is the evolution of your system with time. So, and really depends on what are the goals. Some of the tools might be more suitable than others. So, what can we use? Now, sort of continuum codes. Finite elements will be phase 2, for example. Now is RS2. It's called. Does not exist anymore. RS2 or RS3. rock soil 2D, rock soil 3D, rock science. Flak is not really a finite element, it's a finite differences, it's just the way you solve, but it's a continuum. So those are continuum models where you really assume your model to be continuum and to deform, to plasticize, and eventually some elements they might fail by saying that. Discrete elements, probably the two most used and known are UDEC in 2D and 3DEC in 3D. And then you have particle element codes where instead of having your domain to be divided in blocks, what you have, you say, well, instead of blocks, I use just spheres in 3D or disks, and I put all my disks together, and I assume that the behavior can be reproduced by looking how those disks are moving and are breaking apart. An open source CVR code is called GIAN. And GIAN is an open source, it's a particle code, and then actually it's very nice, there's a big community behind, and it's extremely active, and actually recently I think is developing farther than the commercial code that is PFC. And then here's hybrid code that are generally called as FDEM. That are hybrid in the sense that they solve at the same time the finite elements for the continuum and the discrete elements for the fraction, so for the discontinuum. So it means that they can break the continuum in several parts by using fraction mechanics approach, and by doing that, now you have parts that start to interact and deform. And Irazu is a commercial code that has been based on this methodology, and the Y code is I would say the original one, that is an open source and was initially developed in 1990s, beginning 1994, was a thesis by Professor Muñiz at the time at Swansea. So that is really, I would say, the inventor of the methodology, and then has been developed. And right now, actually, the Y code has a number of different open source projects that are actually widely spread across the globe. And they pick up a lot in China. There are several groups in China that are heavily developing their own version of Y code. So those are pretty much what you can think about for rock mechanics, the main codes and the main tools that you can handle. For finite element, actually, one I forgot that is heavily used, especially for the mining industry, is Abacus. But Abacus is much more, because Abacus has, well, Axis as well, but Abacus has a quite large community behind, and their solver is extremely fast and is allowing the modeling of a full mine at quite a remarkable small scale. So you need to have machines that will allow you that, but Abacus is at least in Australia, Indonesia, Canada, is US, is really heavily used also in mining. And it's a finite element code, it's fully commercial, quite well supported. Okay? Yes. Yes, particle flow, but it's a particle element. I don't like the name flow. That is a brand. So I use particle element. Yeah, what he was saying is that PFC stands for particle flow code. Now, another methodology that is used, especially for if you're looking at slope stability, are the so-called particle hydrodynamics code. So those are instead of having particles, so this you reduce everything to a single dot and springs, and those elements can flow very well. They are extremely fast, and they can reproduce, for example, runouts of landslides or rock falls. Those are other methodologies that you might encounter, might be considering using. Now, all these are slides that I took from Itasca, from one of their presentations. So, what 3-deck or U-deck have been developed? So, Peter Kendall developed this U-deck pretty much during the first version, during his PhD at Imperial College in, I think it was in the 80s, 70s. So, and the idea is that you have two blocks, rigid, and they can interact. So when you're looking at discrete elements, what you're looking at, you have a block, and you need to understand when this block is getting closer and closer to another one. So when it's ready, you interact with the other one, and if it's going to interact, what are the forces that they are going to exchange to each other? So it's a reaction, it's action and reaction forces. Okay? So that is pretty much what you're doing. So you're using the law of motion, translation, rotations, and you allow the contact to have a normal and shear forces. That is pretty much what you need to know as a basics, as an idea. So when they interact, they will create a repulsive force, because if your object cannot really penetrate inside the other. But what does it mean? It means that you need to solve your equations in time. So you discretize your problem in time steps of real time. What does it mean? It means that you need to be able, if I drop this object, to capture where it is time after time up to the point it's going to be closer to the conductor, and eventually start contacting, reacts, and then bumps or does whatever. Okay? So basically you need to be able to discretize your system in a way that you can actually reproduce this one. You can see the object accelerating, hitting your system, and then reacting by rotation and translation. Okay. The problem that you have is that if I discretize this problem in, okay, let's ask you a question. How long since I leave my blue pen to fall, what is the time from here to when I start touching the other one? It's more or less than a second. More or less? Less. So if I discretize my system in 1 second at a time, what I have at the one time step, my pen is here, and the next one is there. Do I capture what is happening at the contact? No. So the problem is that all these algorithms are actually stable if you pick the correct timestamp. So it means that you need to pick a very small timestamp to actually capture what is happening. And in between one timestamp and the other, you don't really know anything. So what it means is that you need to solve all these equations many, many times, once per timestamp. So these equations are basically simple equations, are not system of equations where you need to invert the matrix. It's just that you know your initial state at that timestamp, and pretty much you do solve your equations, right? But the problem is that you need to do this calculation many, 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 many times, and that will slow your solution if your computer is not fast enough. And that's really one of the issues that sort of made the discrete elements not really despite it was the first solution that was proposed, didn't become the preferred one instead of the finite element or the finite differences. And the reason is that these are time explicit, where means that at time you solve your equations really at discrete specific times, while the finite elements can have a solver that is time implicit because they use constitutive models. That means that the time is embedded in the equation and we know how the system behaves with time. Okay? So that's a big difference. So one is, this is time explicit, while most of the other finite element like flag is time implicit. So time is really embedded in the solver. But because of that, you need to solve invert for very large matrices, so that those are bringing you at other different challenges more on memory. While here, for discrete elements, the challenge is that you need to have a very fast computer in the sense that you need to process these equations, solve these equations many, 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 many times. And that is why only recently, with the introduction of GPUs and much faster parallel CPUs, is that you can start thinking about using more and more the discrete elements instead of the finite elements. Okay? So the first commercial code that came out of Peter Kandel was actually commercialized in 1995 by Itasca. That is a company that was funded by Peter Kandel. He was one of the founders. So PFC is another formulation. And what it does, instead of using a block, it decides you discretize everything in particles. And what is the advantages? The advantages basically is that all the contact happens at one single point of contact that can be defined basically only by the distance, the radius, the radiality of the particles, the two particles in contact, and the distance in between the two centers, right? So that means that you can use Earth's contact at the point, and then you need to start adding more and more constraints to actually reproduce what is the shear behavior, the slip condition and the contact, and so far so on. So, great idea, very difficult to actually calibrate because the parameters are micromechanical parameters, means that are very difficult to tie to properties that you measure in the lab. So, you are getting all these equations, so I don't think you need to copy those equations. They are really important. The important part is to understand what is the concept, and the concept is at the end you have spheres or discs, disc and your contact is basically at one single point. And let's skip that. And but the more you try to match what the reality is, the more micro properties you need to have. And that's really what has made PFC extremely complicated to use, and that's my opinion, also very subjective. In the sense that you need to assign properties, but those properties are micro properties, and there are many, and you have no way to measure those. That means that you have more variables or properties that you need to assign than constraints. So generally, if you have 2 equations and 4 variables, how many solutions you can find? Sorry? How many solutions that satisfy your 2 equations? You have 4 parameters, independent. Infinite solutions. So that means that one of the challenges with this type of code is that you don't have only one set of properties that will match your results, but is actually a large number of combinations that can give you actually the same results. And that's it is an issue because what we are interested in is not just the number at the end, is the process that leads to that failure. Because we need to engineer that object, that information, that tandem, that slope. And if the code with a set of properties tells me that it's a shear failure, and another one set of properties tell me it actually is a taut link, that's a problem. How do I going to remediate or try to solve that problem? So, and that is one of the challenges in actually calibrating these type of systems, where you look at micro properties and you have a lot of them. So you need to find additional constraints that will help you to reduce the variability of your properties and to get to pretty much one single behavior, and to have enough confidence on those solutions. The other problem that PFC and all the particle flow, particle element codes have is that when you have a fracture and you break the particles, what you have, if this is your surface, you have quite an inherent roughness that is actually this function of the radius of your particles and the packing. And sometimes is not really reasonable, adds interlocking that is not there at that scale you're modeling. That is why, again, numerically they have been adding solution like, for example, the smooth planes. So what I'm trying to say is that great idea, but when you start to use that for engineering, there are more and more challenges, and iTask has done an amazing work to actually address those. Despite that, they added additional variables that became more and more complicated to use, and to properly use those codes, you need a lot of expertise. So you go from a limited equilibrium like slide, the one that you have used that, to more complex, that is, for example, flat, you have used that is a finite difference, to micromechanical bases such as PLC that is becoming more and more complicated to use, and you need more and more experience and expertise actually to address. Because at the end, what you need to go from single grain to shape, to packing, then you need to use how do you simulate, how do you constrain those properties? Well, you start looking at lab scale simulations, such as biaxial test, Brazilian test, and once that you actually match what is observed in the lab, and you have enough confidence, then you finally use those properties to model whatever is the field scale or the scale of the problems you are trying to solve. And that is pretty much what the path is. So, are we supposed to finish at what time? 12:15? 12? Sorry? So I have 3 more minutes. So, and I pretty much finish here. So, typically, for a PFC, what you are looking at, you have target values like elastic modulus, the Poisson ratio, the strength, the tensile strength, the fracture toughness, and you run your models until you turn all these knobs of micromechanical properties such as you can meet you can actually match what has been observed in the lab. One thing that you should also start looking at is when it fails and the fracture is propagating, if that particular fractures matches what is observed in the lab. Can I give you one single example? One of the tests we are running is a Brazilian disc. So you are loading your disc diametrically, and you should have your fracture that starts from the middle and develops. So it opens in that way and develops along the vertical axis, the loading axis. That is what Brazilian disc, how the Brazilian disc fails. And these bonds between your particles should fail in tension. So if you interrogate your model and you see that it fails in shear, you might match everything there, but the process that is resulting of your model is actually not matching what reality is. So that means that you might have found a combination of parameters that actually match the values but does not match the behavior. And that is where you need to pay attention. You need to make sure that it's not just matching the number, but also match the behaviors. And that's really the tricky part for any micromechanical model. And that is where you, as an expert user, you add in the value. It's not just building the model and assign the property and knows where the menu is, but it's actually looking at the results and ensuring that those results are correct. Okay? And that is what is very important. You need to learn and understand. The value is not that you know what the menu is, what that particular function is. From your experience and what you have been studying is the interpretation of the model and understanding if that model is correct or not. At some point, you will forget what the menu is, but you see the results and say, yes, that's correct. No, that's not correct, without even running it. And that is what you are here, what you're doing, you're studying for, is not to learn how to use the model. That could be probably done at almost undergrad, if not high school level, is to understand if those models are correct or wrong. And that's the only reason why you want to do numerical modeling. And once that you know that, your potential, what you can do is huge, because you can start having confidence in your models and start addressing questions that are really pertinent in the profession. But unless you're able to interpret correctly the model and to see if it seems right or wrong, well, you need to keep on studying. Okay? And micromechanics, the more complex the model is, the more difficult and more involvement from your side works. And very often, you have no clue if the model is right or wrong. So you need to sort of simplify the model to check if the set of parameters you have chosen actually match that simple model. And only at that point you can extrapolate for the larger scale. Okay? So now we're stopping here, and this afternoon the plan is a little bit different. What we're going to do is, what I want is really to present what we are doing and how we can extend this concept micromechanical model through the hybrid codes, and specifically this finite element, discrete element code that personally, well, we'll be developing that, so I'm very biased, but I like to think that we are not anymore the only one. The community behind it is growing. So I think those are the type of code that you need to be exposed at your specific stage of the career, because those are the future. And just to sort of justify that, the International Society of Rock Mechanics awards every year a PhD award that's called Russia Medal for what they decide to be the best PhD thesis worldwide done in rock mechanics. Out of the last 5, 4 are actually have been awarded to people that were students that were developing or using FEM, finite element discrete element. So it's actually is happening. There's a big value. It's not just because me say that, but it's sort of a common agreement that is the next step. It's not just because of the beauty of the system, not just because the physics that is implemented seems to be more correct, closer to the reality, but it's also the reason that is taking place is that the computational power that is available nowadays allows us to use micromechanical models to address much larger scale. So that is what I really want is the last few hours that we're going to spend together will be really focusing on that, and I hope we'll spark a little bit of interest and questions on these methodologies that, in my opinion, are going to become not anymore the cutting edge research, but will move or are slightly moving towards becoming the standard tools in the industry. Just to finish, some mines are actually using them for their, for example, slope pit design, for the slope stability. So it's not just a research, it's actually bridging into practice, and specifically mining. So see you at 3:30.